Hello, dear students. Welcome you all. In this lecture, I am going to discuss in details about the concept of Fermi energy and Fermi energy level, right? Fermi energy and Fermi energy level, right? You might have heard this word Fermi energy or Fermi energy level many a times, whether it is the discussion of the semiconductors or it is the discussion of conductors or it is the discussion of insulators. This Fermi energy level or Fermi energy plays a very vital role in understanding the conduction property of all the materials, right? To understand it, what is Fermi energy and Fermi energy level, let's consider that we have a material, right? Let's consider we are given a material, right? Let this is the given material, right? This material obviously contain large number of atoms. Clear? Now, these are the atoms. Clear? Now, I'm talking about the individual atom, right? Let this is the individual atom of this material atom, and this is a given material. Clear? Now I'm coming to the individual atom. You look at the individual atom. Clear? This is the nucleus. Now, when we start filling electron inside an atom, we know very well that electron will start entering the atom from the lowest energy states. So if I draw the energy states in this manner, right? Right. This is the ground state, lowest state. This is the first energy state. This is the second energy state. This is the third energy states. Clear? This is the fourth energy state, and so on. Clear? And so on. Right. All these are the energy states starting from the lowest energy state. Clear? This is the zero energy, and as we move upward, the energy increase, right? You can see from this picture at that as we proceed upward, the energy levels are coming close and close, right? This is the situation of all the materials, and it has been proved mathematically as well as theoretically that this is the situation in case of materials, right? Energy levels are arranged in this manner, right? So let it is n is equal to 1, it is n is equal to 2, it is n is equal to 3, it is n is equal to 4 level, right? So when we will start entering the electrons in this in these energy levels, right? Sorry, there is a rule called Pauli's exclusion principle. Clear? We know we have discussed it in the earlier lecture also. So according to Pauli's exclusion principle, only one electron can enter into a one cell. Clear? If we assume that this cell, that is this first cell, I'm calling it as energy level 1, right? Let this can accommodate two energy cells, right? So the maximum electron that can enter in this first energy cell are obviously 1, 2. Similarly, in the next can also accommodate this way, right? If I go on filling the electrons inside this material, then the electron will start filling from the first energy level, then second, and then so on, right? We can have an electronic configuration like 1s2, 2s2, p4, right? In this way, we can have so on 1s2, 2s2, 2p4, 3s0, so on. This is the configuration. This is the way we can put up all the electron inside the atom. But the thing is, as we go on adding the electrons inside the atom, the electron will start entering that atom from the lowest energy state to the highest energy state. Now let the outermost electrons are present in these two states. Clear? Now if they acquire energy from some any mean like a temperature or from radiation, then even they can excite to the higher energy states. They can go to the upper energy states. They can present there under normal temperature, right? Now what I am going to do, now I am going to reduce the temperature of this material. Now if I reduce the temperature of this material, then the electron will try to occupy the lowest possible energy states which are available for them. So in that situation, as I go on decreasing the temperature, the electron will go on returning back to the original positions, and ultimately at a temperature of 0 Kelvin, a situation will be reached. In that situation, there will be an energy level, right? Like this is that energy level, right? I can say this is the that energy level at t is equal to 0 Kelvin, at which this energy level, all the energy level toward this side are fully filled. Clear? Whereas all the energy level above to this level are fully empty. Clear? So now this level, this energy level that separate the fully filled energy levels from the fully empty energy levels is called a Fermi energy level, right? So Fermi energy level is defined at that level below which all the energy levels are fully filled and above which all the energy levels are fully empty, but at a temperature of 0 Kelvin. Now if I increase the temperature, in that situation the electron will try to go to the higher energy states, and in that situation we can't say that there is a particular level that separate the filled level with the empty level. So in that situation we make a approximation that will be cleared in the upcoming part of this lecture. But this is the situation of an atom, and this is the situation at 0 Kelvin, right? So now one thing is clear, that Fermi level is what? Now the energy corresponding to this level, that is EF. This energy is called a Fermi energy, right? This is Fermi energy, the energy corresponding to the topmost filled level at 0 Kelvin, right? So this is Fermi energy, right? Now I am coming to the case of a material. So this was the case of a atom, right? You can see here. Now when large number of atom join together with each other in a material, right? Then obviously their bonding take place and the atoms are get influenced by their surrounding. So what happened? Now the atoms, clear, when they get influenced by the surrounding, their electron don't have specific energy in particular orbit, but rather they will have a range of energy. That range of energy of the electrons is called energy band, right? So then energy levels get converted into energy bands. I am showing you the diagram of drawing the diagram of that energy bands. Right. This is one energy band. Similarly, this is the next one, right? Similarly, we have now all these are energy bands. Energy band means range of the energy possessed by the electron inside this material. So this is like this is the the band, energy band that contain the valence electron. Clear? This band is called valence band. Valence band means that band which contain the valence electron, topmost filled energy level electrons. So that band becomes valence band. The band immediate above to this band is called a conduction band, right? And the region between these two bands is called a forbidden band. So this concept is very important in semiconductors, right? And when we are making the distinction between semiconductor, insulator, and conductors, right? So here you have seen that how this energy level concept got converted into energy bands in case of material. But when we are talking about individual atom, then this is the situation, right? So now when this is the situation, then again in this situation, under normal temperature, there is not a fixed level or band that can separate the filled levels or filled bands with the empty bands. So in those situations, the Fermi level is just a imagination, right? It is just an approximation that it lies somewhere, just like it is present here. So it will be, in that case, it will be a approximation, right? So now I am going to uh, make this discussion in terms of a Fermi Dirac distribution function, because we know Fermi Dirac distribution function tell us about the distribution of the energy of electron, right, in a given material, particularly conductor. So right, so we know very well what is Fermi Dirac distribution law. That was N E D E is equal to not Fermi. This is not this is wrong. It was Ni upon Gi is equal to 1 upon e raised to power alpha plus beta E I plus 1. So this is actually Fermi Dirac distribution function. Clear? So first of all, I am going to make the discussion about it, right? If I take the case of particular energy E, then it becomes Ne upon Ge is equal to 1 upon e raised to power alpha plus beta E plus 1. Clear? So this is the case now. Now this, what is this? This is basically the ratio of the number of electrons in the energy range E to the number of phase space cells in this. So this is called Fermi Dirac distribution function, FD, right? I'm calling it as capital F, and I'm writing it FD, right? This is equal to this, right? So here we have to put the value of alpha and beta. We know what is the value of beta. It is 1 upon kT. Now the value of alpha has been calculated in terms of Fermi energy, and it comes out to be alpha is equal to minus EF upon kT, right? Now, it is beyond the scope of this course here. It has been calculated in quantum mechanics, and it has this value. So, I'm going to directly using this value in this equation. So, when I'm going to put this value here, all these values here in this equation, that it is equation number 1, then it will become uh, F FD is equal to 1 upon e raised to power minus EF upon kT plus E upon kT. Clear? Plus 1. Right. So when you will simplify it, it will become 1 upon e raised to power E minus EF upon kT plus 1. Right. This is Fermi Dirac distribution function, right? And this is very important. Now I'm going to make the discussion on this equation, right? At different temperatures, right? At different energy levels. I want to see what is the physical meaning of this equation. This is equation number 2, right? So we will take the different conditions. First of all, we will take the condition when T is equal to 0 Kelvin, right? So when T is equal to 0 Kelvin, two situations are there. Either E greater than EF or E less than EF. Clear? When T is equal to 0 Kelvin, you can see here. If T is equal to 0 Kelvin means we have 1 upon e raised to power e minus ef upon 0. So it is going to become infinity, but it depends. If e is greater than ef, then it is a plus infinity, right? And here it is also plus 1. So if e is greater than ef, then it is plus infinity. E raised to power infinity tends to infinity. 1 upon infinity tends to 0. So in this situation, this term become a 0. It means fd is equal to 0. Means if temperature is 0 Kelvin, then all the energy states above Fermi energy level are fully empty, right? Now the second case, when E is less than EF, then obviously it is negative. E raised to power in minus infinity tends to 0. Then 1 upon 0 plus 1 means 1. So in this situation, it becomes a 1. So FD is equal to FFD is equal to 1. So this is very important. It means when temperature is 0 Kelvin, then all the energy levels below Fermi energy level are fully filled. Because this term FD, this is telling us about the probability of occupation, Ni or Ne upon Ge. What is this? This is the probability of occupation. It is 1 means all the energy level are fully filled. If it is 0, it means all the energy level are fully empty. So this is the first case. Now come to the second one. When T is greater than 0 Kelvin, right? And E is equal to EF, right? Because we can't take E is equal to EF and T is equal to 0 Kelvin at the same time. In that case, this equation will 0 upon 0, undefined, right? So we are now considering the temperature T greater than 0 Kelvin, sorry, here, and E is equal to EF. So when E is equal to EF, in this situation, it is 0, e raised to power 0, 1, 1 plus 1, 2. So what is FD? Now it is equal to 1 by 2, means 0.5. So what does it means? It means when temperature is greater than 0 Kelvin, in that case, the Fermi energy is that energy level at which the probability of occupancy is 50%, right? Means there are 50% chances of the energy level to be filled, right? As we go above the Fermi level, these chances go on decreasing, but as we come down to the energy level, EF Fermi level, these chances go on increasing. So in that temperature range, the Fermi level play a different role. But when the temperature is 0 Kelvin, then this level is very clear that at that level, fully filled, below fully filled, above empty, right? So I'm hopeful that this thing is very clear. Now I'm going to plot a graph of a Fermi Dirac distribution function versus energy, right, in the two situations. Right, this is F FD, Fermi Dirac distribution function. This is energy, right? So this graph corresponds to, this is one value. One means when temperature is equal to 0 Kelvin, right? And when T is greater than 0 Kelvin, this is the graph. When T is equal to 0 Kelvin, E is equal to EF, right? So at up to this level, all the energy level are fully filled, and toward this side, fully empty. Clear? This is the situation of a temperature 0 Kelvin. But as the temperature is greater than 0 Kelvin, then this graph becomes like this. Right. Now, in that case, this is the value of 0.5. Clear. So, in temperature range greater than 0 Kelvin, right? This is the graph for this function, right? So in that case, now the Fermi level is that level at which the probability of occupancy is 50%, right? So this is the graphical, or I can say pictorial representation of what we have discussed here, right? What we have discussed here, this is the pictorial representation, right? And I'm hopeful that the concept of Fermi energy level, and Fermi Dirac distribution function is very clear. Now, what is the next step? In the next step, we are going to put the value of alpha is equal to minus EF upon KT that I took directly, and now I'm going to put this value in the equation NE dE is equal to 8 under root 2 pi B upon h cube into m power 3 by 2 e power 1 by 2 dE upon e raised to power e minus ef upon kt plus 1. Here I put the value in this equation that we have written earlier. Earlier it was what here? It was e raised to power alpha plus beta e plus 1, right? This was the term, this term, right? So now when I put value alpha is equal to minus ef upon kt, beta is equal to 1 upon kt in that expression that we had derived in the earlier lecture, then it becomes this. Right. Now, when I will simplify this equation, then this will convert into now we are going to simplify it by applying the condition T is equal to 0 Kelvin. Sorry, 0 Kelvin. Now at T is equal to 0 Kelvin, right? The number of energy states occupied by the electron, right? That is from 0 to energy EF, right? That will give us the number of electrons, right? If we say that one electron is accommodated in one energy level, right? So in that case, all the energy states from this from 0 to EF, they will tell us about the number of total electrons, right? So we can see how it is possible. So n is equal to integration 0 to E F N E D E. So what I said that when the temperature T is equal to 0 Kelvin, then all the field states from 0 to EF, if we assume one state contain one electron, then these states will tell us about the total number of electron present in the system, right? So when I put the value of NEDE from 0 to EF integration limit, right, then this value will come here obviously, but in the limit of E to EF and T is equal to 0 Kelvin, this factor is equal to, right? This entire factor is equal to 1, right? We have seen it here, right? FD is equal to 1, right? When E is less than or equal to EF, it is equal to 1, right? So in that case, it will become your integration 0 to EF, right? 8 pi 8 under root 2 pi B upon H cube M power 3 by 2 E power 1 by 2 dE, right? So now this factor becomes, whole factor becomes 1, right? Because it becomes 0 and it becomes 1, so this entire factor is 1. So now this is the term that is left here. So now n is equal to 8 under root 2 pi V upon H cube M power 3 by 2, right? Integration 0 to EF, right? E power 1 by 2 dE. So when I will take this integration, it will become E power 3 by 2 E power 3 by 2 divided by 3 by 2, right? Whole term limit 0 to E. So I can simply take here EF because the second term will become 0. So now I can erase these limits from right. So now this is the case, right? So now I can further rearrange it. Then n is equal to 16 under root 2 pi V, right? m power 3 by 2 divided by 3 h cube ef power 3 by 2. So when I take this toward this side, then I will get ef power 3 by 2 is equal to 3n h cube divided by 16 under root 2 pi b m power 3 by 2, right? So this is the expression. Now if I take this power toward this side, then it will give me ef is equal to, you can solve it, h square upon 2m into 3n upon 8 pi b power 2 by 3. Now this is the required expression. When we will solve it, you can do it by taking this power toward this side. So this is now the required expression for a Fermi energy, right? You can see here that the Fermi energy EF depend only on the mass of the fermion, and N upon B means the density of the free electron in that material. It is independent of the temperature of the material, right? It depend only these two factors. Mass, if we take M also constant, then it simply N upon density of valence electron, density of the free electron per unit volume, right? So this is it becomes a now inherent property of any material, right? Because N upon V is fixed in any material, right? So every material has a particular Fermi energy, right? So this is the expression for the Fermi energy, and this is the dependence of Fermi energy on these two factors, right? So now I am going to write down the Fermi energy of a few materials, right? For example, if we calculate the Fermi energy of material by using this formula, then for example, cesium, it is a 1.58 electron volt. Similarly, for copper, it is a 7 electron volt. You can have different examples, right? You can have example of gold, right? For gold, it is a 5.51 electron. So you can calculate the Fermi energy of different materials by using this relation, right? So this was about the concept of Fermi energy level, and the derivation for Fermi energy, right? So this is all about it. So thank you very much.